Sorry, well, yeah, apparently I'm going to be my MC. Hello, everybody. Woo! You ready for some math? I can't hear you. Are you ready for some math? Woo! All right. It is amazing to see the crowd here today. I mean, wow, ZK Summit 10. I'm amazed this thing still exists in 2023. But all credit to Anna and her team, amazing stuff. I was there for ZK Summit 2, that was my earliest one, where wow, things were very, very different. It was more of a, less Paul more hole in the wall East Berlin, bit communist, bit Soviet, but the vibes were great. And it's amazing to see so many people from there still with us today. And wow, how things have changed. I mean, did you know that tickets on the door here, £650? Incredible. I've been doing a bit of online dating, met someone through Hinge, had a few nice dates, it was enjoyable. Then, yeah, so she was like, for the next date, take me somewhere expensive. So, yeah, she's not returning my calls anymore. Okay, well, before I get into the meat of this talk, I have an announcement to make. Quite a special one, really. So I've been in this industry, working in ZK privacy with Aztec for 6 years. 6 years before the mast. And for all that time, the shining city on a hill, that beacon that we've been aiming for, has been programmable privacy. The ability to transact in a decentralized peer-to-peer manner, either between individuals or small groups, without intermediaries, without revealing who you are or what you're doing. We've always realized from the very start that it is the apotheosis, in my opinion, of blockchain. If you think about the original cypherpunk vision from 2008 of what blockchain could be used for, the global settlements layer, everyone's going to be using Bitcoin, everything's going to be a digital asset. Well, it's been 15 years, and let's be honest, it's not really come true. I like Bored Apes as much as the next person, but it's not quite what we were imagining all that time ago. And I would argue that the reason for that is because we do not have privacy. Without privacy, you do not have the ability to link an identity to a cryptocurrency account. Without that, you cannot link cryptocurrencies with real-world assets and with the actual sources of value that people are transacting with in their day-to-day lives. And privacy solves that. And why I am talking about this, just give me a second, is because we have an announcement to make. After a lot of work and a lot of effort, we have finally been launched the Aztec sandbox. So the Aztec network is being designed as the end game for blockchain privacy. It is one of the most, if not the most ambitious and complete solution for privacy-first blockchain applications that has ever been attempted. It's taking us a hell of a lot of time to get here. We've had to invent our own goddamn cryptography to get here, but we're getting there. And as previously mentioned, building this sandbox is taking just 5 months. Only 5 months from inception. And it's a testament to the quality of the Aztec team, to the dedication of my colleagues, my team members, and the ever-improving modularity of our technology, our open source technology. The sandbox is our first major milestone in the development roadmap that includes a multi-phase testnet for Aztec, and our execution environments, our fee model, our sequences, our provers, all culminating in a privacy-preserving ZK rollup that is fully decentralized at mainnet launch. I need to click. Too many things. I'm going to move over here. Yes. So, the sandbox is effectively a local developer testnet, a development environment for private smart contracts. And what does that mean? That means you've got private function execution, public function execution, and composability between private and private public link, composability between L1 and L2, the ability to create hybrid applications, private state management, hidden function execution. It looks and quacks like a blockchain, but you have private state as a first-class primitive. And that's what comes in the box, alongside our local node testing environment, our RPC servers, and the frameworks that allow developers to compose useful, meaningful transaction flows that involve privacy, which is a very new kind of pattern. The sandbox helps future-looking developers get a head start with ZK-native blockchain environments. We have concepts like private state, account abstraction, understanding the patterns that keep private information private, and organizing contracts into the private and public executable logic components. And so what I want to say is, well, you can get started in 10 minutes at sandbox.aztec.network. That is the, wait, no, I didn't click, sorry. I didn't click. Sandbox.aztec.network. We've launched, and tomorrow, tomorrow on Thursday, we are doing a developer workshop right here in London. That QR code will get you a sign-up link. So if you want to start working with programmable privacy tomorrow, scan that QR code. No, I don't see enough phones scanning. We might need to change that. Genevieve, could you help me out here? I think we might need a bit of motivation for people. I don't see enough phones scanning the QR code. All right, who wants an airdrop? Who wants a goddamn airdrop? Woo! All right, there's more where that came from, but it takes us a while to load. All right. Can you hear that? Seriously, this has been the combination of so much work at Aztec. You know, we've been trying to do this for 6 goddamn years. A lot of stuff in between Aztec 1, Aztec 2. So, you know, we're going to put the concussion back in ZK. Right, on with the rest of the talk. Oh no. Okay, if any Aztec folks are here that can help with that or sort it out, or if maybe there's just not enough space, I'm sorry. Well, I think we're live streaming it too. What the bloody hell is Honk? That is a question, one of the questions in the planet today. So Honk stands for highly optimized Plonk. And it's our attempt at creating a composable smart crypto system that is very, very privacy-friendly and privacy-first. And what I want to talk about today is a little bit about how it's built, its techniques, what we're using it for, and how it's been made. So to start with, what are the 4... Like, the zkSNARK landscape has become fantastically complex lately. There's been an enormous amount of research into new protocols, new techniques, and we've been building layers upon layers upon layers of abstraction layers to enable us to increase complexity and increase proving speeds, verifier speeds, proof sizes, etc. But this comes at a bit of a cost where everything is so complicated now, it's very difficult to see how things actually work end to end. Very rarely these days do you get an actual paper which describes a protocol where it literally lists out the protocol. It says, here is an interactive protocol between a proof and a verifier. Do this, do this, do this, do this, do this, because there's just so many abstraction layers and complexity, it's very hard to do. So I want to break some of that down today and talk about how we create an end-to-end SNARK in the modern world with all of the new techniques. And so this is what I think are the 4 kind of main key abstraction layers, pillars of modern zkSNARK. You start with your circuit arithmetization. That's effectively, how do you represent your program as algebraic relations? What are those algebraic relations that you are evaluating? You then compile that into a polynomial interactive oracle proof. So a PIOP will be an interactive protocol between a prover and a verifier that will validate the correctness of your arithmetization for a given instance. And here is where a lot of the complexity lies in modern protocols. There's lots of ways of doing it. And then finally, your PIOP is going to reduce the claim about the correctness of your circuit to a claim about some evaluations of committed polynomials. And we use polynomial commitment schemes for that. And there as well, there's a huge design space, mostly between error-correcting code-based schemes, hash-based schemes, and additive groups, basically, elliptic curves. And finally, you have the folding schemes, which, as Anna has beautifully elucidated, are somewhat complicated. Yeah, so Honk is basically a parameterization of all 4 of these using various different choices and selections, and I want to talk a little bit about it. It's a SNARK for people who care about privacy still. There's not many of us these days. So just a quick recap of what is it that we want our cryptography to do. We have Aztec contracts are composed of functions. These functions are effectively individual SNARK circuits. And a user transaction is a set of SNARK proofs that represent all of the functions that have been called within a transaction. You then need another SNARK circuit, kernel circuit, that will effectively verify the correctness of all these proofs and validate the transition functions between all of the proofs to verify that all the calls are correct. This is very complicated, specifically because this kernel circuit, with all of its intense recursion, needs to be computed client-side if you care about privacy, because otherwise you leak secrets. And that means that these proofs are being computed on wimpy consumer hardware, like phones and laptops. And not only that, but the proving environment is probably WebAssembly, because if you're interacting with a DApp in a web browser, that's what you're going to get. And so those are insane resource constraints that are absent if you are capable of delegating proof computation to a third party. And that has knock-on effects for how the proving system is built, because you care greatly about memory consumption here. You care greatly about things like recursion, not only because the architecture isn't inherently recursive, but because you can use recursion to reduce memory consumption by breaking down your program into smaller chunks and iteratively proving them. So what is Honk? How do we do this? So on the arithmetization layer, we use ultra-Plonk, which is effectively Plonk with plus and gates, lookup tables, like RAM tables. I can get into that in a bit. Very efficient range checks. It's basically all of the tricks thrown in. But it's relatively, the actual arithmetization is pretty old these days. The IOP we use is a sumcheck protocol over multilinear polynomials. Very different from original Honk. Much faster, it's linear time. And then we use the zeromorph, multilinear polynomial commitment scheme, to evaluate these sumcheck claims. This was one of the effective multilinear PCSs, one of the things that make multilinear sumchecks a lot more useful these days. And then finally, we use the proto-star folding scheme. We use proto-galaxy because we fold multiple instances, but proto-star, well, they pioneered this concept. And then finally, we use goblin Plonk as there's not really a word for it yet, but it's a folding accelerator. It makes the complicated, hard-to-do operations in folding schemes very efficient and cheap. So these are some of the performance targets that we have for Honk. We want our prover to be able to prove 1 million constraints in less than 5 seconds. Doesn't seem too hard, except that our prover is a phone and it's running WebAssembly. We have a gigabyte of RAM, not a terabyte, a gigabyte, which is rubbish. Web browsers have a habit of killing tabs if you use more than that. Proof size needs to be small, because we're a transaction network, a layer 2, which means that users are sending their transactions to a mempool. If each transaction carries a zero-knowledge proof, and you want a very high transaction throughput, and you want your nodes to be decentralized, so any random person can run a node, that means they need to be able to, your network bandwidth cannot supersede an average board racking connection. So at 1,000 TPS, you can't have 100 kilobyte proofs. And finally, we need our recursion folding cost to be absurdly cheap. We're targeting proof construction times of 20 milliseconds for recursion in WebAssembly. So these are some rather weird requirements that you don't get from transparent systems. In terms of asymptotics, what is Honk? I mean, I don't know. I mean, to be honest, I can probably make these numbers say whatever I want to. The thing that really matters is the code and actually what it really does. But you can get a variant of Honk where, in terms of elliptic curve costs, the commitment cost is equal to the number of unique wires in your circuit, removing copies. And then it's linear time in terms of fieldwork. So now I want to dive a little bit down, peel back those abstraction layers, and talk about these components in a bit more detail. What is like the multilinear sumcheck protocol? I was speaking at, what was it, Barcelona or something, realizing that actually, whilst in my head, this has been a big deal and a very, very useful tool, it's not really like that widespread that this is like amazing, and that you want to use sumchecks in a multilinear form if you're evaluating complex expressions. And that's because it's, despite being a very, very old technique, all the problems that were associated with it have been solved. And it's very, very efficient. The idea is you have a bunch of input polynomials. They can come from your input string, your witness string. They're in multilinear form. And by multilinear, I mean the maximum degree of each variable is 1. And you have some expression of your polynomials that you want to evaluate. And the idea is that what a sumcheck will do is you can sum over all of the possible evaluation points of your polynomials over some domain, in this case 0 and 1. And you check that the expression applied to those evaluations, and then the sum of all the various different evaluation combinations, you check that's equal to 0. And this is very easy to adapt into a system where you can check every constraint in a Plonk-ish type circuit or RMCS is 0 by adding random polynomials in to make sure that you have linear independence. How it works, it's pretty straightforward. But for those who are unfamiliar, the idea is that you have a logarithmic number of rounds where you basically reduce the degree bound by 1h round. The idea is the prover computes these univariate reductions where you evaluate your expression over your entire domain, apart from for one variable, which you leave as indeterminate. That becomes your univariate polynomial, gets sent to the verifier. The verifier checks that that polynomial u at 0 and 1 is 0, because that's the sum of everything on 0 and 1 is supposed to be 0. And then the verifier will generate a challenge. And then we just iterate. The idea is now the prover produces a new univariate, except that that indeterminate variable is now being replaced with the random challenge. And you now make one of the additional variables indeterminate, and you reduce the degree bound by 1. And you compute that new univariate, send it to the verifier checks that new univariate at 0 and 1 equals the previous univariate at the previous challenge. That provides a continuity check between each univariate reduction, and eventually, once you perform log n rounds, you will get to a relatively straightforward expression where there will be a claim that your polynomial identity evaluated at a series of random points will equal a constant field element. You can then check that with something like a polynomial commitment scheme. Once you have that, you then need to move to, what kind of commitment scheme? We use zeromorph. So multilinear PCSs have always been painful, like logarithmic numbers of pairings, blah, blah, blah. Recently, there's been a bunch of solutions where basically you just compose a multilinear PCS out of a univariate one. Gemini started this first. Zeromorph is an attempt at generalizing that and adding some efficiency tricks. It's pretty efficient. And the idea is pretty straightforward. Once it's been developed, it was a brainchild of Tori, one of our researchers, is that there's a linear isomorphism that's trivially computable between the multilinear form and the univariate form of a polynomial. So if you have some kind of linear relation over multilinear polynomials, you can convert that to a linear relation of univariate polynomials by applying this isomorphism. And it just so happens that the multilinear KZG polynomial commitment scheme, the relation that's being checked is linear, is a linear expression. So you can basically take multivariate KZG and apply these isomorphisms to evaluate it over univariate polynomials and compile everything to a univariate PCS. Very efficient, very nice. And then we get to folding schemes. So I think there's going to be some talks later today that will explain this in far more depth than I can or will, but at its core, the idea is you have, instead of having a large number of proofs that you then construct independently and verify independently, you take the input string, witness string tuples that describe a relation that you want to prove, and you take a set of those, and you fold the input string, witness string tuples together to create a new relation. So the idea is instead of having a prover and a verifier, you now have a prover and incremental verifier to verify the folds and a decider, which was what your original verifier would be. The idea here is that the amazing thing about things like protocols like Protostar is that they are very black box. They can fold any arbitrary interactive protocol as long as it can be categorized in this relatively straightforward structure where you you have an input string, witness string, you have various rounds with messages and challenges, and as long as you can fit into that structure, you can fold it with Protostar. It's very, very powerful. And basically what it will do is it will you define this randomized relation, which is basically like your original relation, but with an error term. And what folding schemes will do is they will take an instance of a randomized relation and multiple instances of the relation you want to fold, and will spit out one instance of your randomized relation. And the verifier for that is very cheap and very effective. So I have some slides here about how our circuit arithmetization works as well, because there are a few little tricks that we can use. I'm going to skip over these a little bit because running out of time, too many shots with a cannon. If you want to ask me questions after the talk, very happy to. But this is basically relatively standard UltraPlonk stuff. But what I wanted to highlight is that there are some tactical tricks that we use in UltraPlonk that have not been widely disseminated, which is worth talking about. Specifically, you can get super cheap range checks with Plonk-ish type systems. You can get things like RAM and ROM tables, dynamically accessible, resizable arrays by manipulating the permutation argument. Basically, you take the original Plonk permutation argument. You can imagine you have cells in a Plonk circuit. In your execution trace, highlight some cells in red, some cells in green, and you can efficiently prove that the set of the red cells is equal to the set of the green cells, the values, that is, by manipulating the permutation, just tweaking some of the values in your selected polynomial. So it's effectively free. And then you can use that to create things like cheap range checks. Let's say I want to range constrain the purple cells. I want them all to be less than 2 to the 16. I will copy them into a new region of my circuit, that blue region. I will apply a list equivalence check to prove that those two regions contain the same values, but the blue one is sorted. I will then apply arithmetic constraints or custom gates to validate that those blue cells are monotonically increasing in value, and check that the first one starts at 0, the last one ends at 2 to the 16 minus 1. I've skipped out a few things here. You need to add a few dummy wires as well, so you can traverse this range. But ultimately, you can create a situation where doing a range check like a 60-bit range check effectively costs the prover one group addition. Not a scalar multiplication and addition. I can talk about that after the talk. And then we have ROM and RAM tables. This is relatively old techniques from like ARIA and TinyRAM, but the idea is you take a table entry is a tuple of index value and timestamp. Timestamp is kind of when in your circuit trace you're performing a read and a write. And you can use this list equivalence check to effectively copy the set of all of your table reads into a new sorted set where everything is sorted by index, and then within that index, entries are sorted by timestamp. And then you can effectively, if you have, you can compare pairs of rows, and if the second row is a read operation, you can assert that the values of the two rows have to be equal to one another, and that gets you RAM access. Effectively, you can get it in 2 or 3 Plonk-ish constraints, or like 10 columns or 9 columns, you can validate the correctness of like a dynamically resizable array. We use it in Noir, we use it in Aztec, it's super powerful. And then finally, we have lookup tables, which I really do not have time to go into, but very powerful. There's loads of new techniques that come out. But what I really want to go through is a couple of open problems and new trends that we've observed cropping up, some of the exciting stuff that's happening. First of all, folding schemes are a big deal. They massively change the protocol design space because it introduces efficient and easy amortization. Effectively, you can take an interactive protocol with a very expensive verifier algorithm and use folding to turn that into an expensive decider algorithm. And then you can fold a large number of instances of this protocol using a cheap incremental verifier and effectively amortize away the cost of that expensive decider. Every protocol gets some of this for free. For example, with Plonk, when you use a folding scheme, you don't need to provide polynomial opening proofs for every single instance anymore, and that's a big deal. But the technique can extend to much more complicated scenarios, and it's extremely powerful. The other one is that GKR is a big deal. So this is, again, a relatively old protocol about creating layered arithmetic circuits, where you have this kind of recursive relation where previously it's been considered that you have some layered arithmetic circuit where the output wires of the current layer equal the input wires of the previous layer. But I believe that technique can be generalized considerably. And effectively what you can end up with is a scenario where any interactive protocol where the prover is sending messages to the verifier that can be derived from other messages, you can eliminate those messages and the commitments that are sent along with them. For example, with Plonk, you can remove the ground product polynomial. With lookups, you can remove the log derivative, inverse polynomial. It's extremely powerful. But it's also an open problem to make it efficiently foldable because I believe currently folding GKR instances gives the incremental verifier a log squared n cost in terms of hashing because the GKR protocol is log squared n, which is rather painful. So before I go, sorry, I think I might be running over slightly. 1 minute. I mentioned before, it's very rare these days for a protocol to be just like written about where you actually have, where the write-up will describe an interactive protocol between a prover and a verifier that will just say, do this, do this, do this, do this, do this. So I figured I'd have a go for Honk. And once upon a time, there was a psychological horror. This is just the first page. Yeah. So yeah, this is why they aren't written out anymore. The end.